Hello everyone, I'm Chen from University of Maryland. Today I'm presenting our work called Mystique, Deconstructing SVG Charts for Layout Reuse. The work was done by collaboration with Bongshin from MSR, Yunhai from Shandong University, Yunjeong and my PhD supervisor Zhicheng from UMD. Data visualization creators often search for and incorporate existing visualizations in their work, because these visualizations serve as concrete examples that embody design ideas in terms of encodings, visual styles, and layouts. Numerous visualizations are available online, created from visualization languages such as D3 and VEGA-Lite, and authoring tools like Data Illustrator and Charticulator. However, it remains challenging to repurpose these visualizations with new datasets. Users need to either learn the programming constructs provided in a language or understand the underlying framework of an authoring tool first. To this end, there has been a thread of research such as D3 Deconstructor and Chart Reuse that focuses on deconstructing existing charts and then reuse them on new datasets, instead of starting from scratch. However, there are two major limitations that persist in these tools. They are mostly tool-dependent and focus only on styles rather than layouts. To be specific, D3 Deconstructors works for basic charts like bar charts and scatter plots created with D3.js, and Chart Reuse handles infographic bar charts from PowerPoint. As a result, complex visualizations such as small multiples and charts with nested layouts or from other charting tools are not supported. To address these limitations, we extend existing work and investigate deconstructing charts of the tool-agnostic SVG format for layout reuse. To form a feasible and concrete research problem, we investigate the Beagle dataset, which reflects the general population composition of online SVG charts, and found that rectangle-based charts account for the largest portion, encompass various chart types, and afford the most diverse chart layouts. We thus decided to focus on rectangle-based charts in this work. Next, I will present a short demo on the Mystique system to repurpose this tree map group bar chart with the dataset of the sales record of a store. The chart uses a hybrid layout design, where the overall grouped bar chart representation shows trade values in different years, with the bar height encoding the total value. Within each bar, a two-level tree map shows the proportion contributed by each country, colored and grouped by continent. Currently, the only way to repurpose a chart of such bespoke layout is to program using libraries like D3, and it requires deep D3 expertise and significant time. With the chart imported, Mystique first applies a set of heuristics to detect reference objects, including axes and legend, and display recognized labels and data types. The user notices that the x-axis has two levels of labels, and the y-axis labels are numbers. So they click the plus button to add a second level display box and drag the year labels into it. Then select number to be the y-axis data type. After clicking the next button, they enter the Reuse UI. The Reuse UI shows the given example on the bottom left, the working visualization being edited on the top canvas, the dataset panel on the bottom right, as well as instructions on the required datasets and the reuse step on top of it. Mystique first asks what the highlighted highest level tree map bar group in the canvas should represent in the dataset, and grays out other parts of the visualization. The user then selects category, and the chart is updated to reflect category's values. Mystique next asks three similar questions respectively for the first tree map bar, the yellow-colored rectangle group, and the first individual rectangle. The user selects subcategory, region, and order ID in response. Then Mystique starts handling encodings. It first guesses that the height of each tree map bar should represent cells, which is accepted by the user. Next, it guesses that the fill-in color of each rectangle should represent cells, which is corrected by the user into region. Lastly, the user accepts Mystique's guess on the error encoding, leading to the final chart on this new dataset. Here is a pipeline illustration summarizing the human-in-the-loop workflow in the demo video. Mystique first preprocesses a given SVG chart to obtain a set of visual objects with accurate property values, then applies heuristics to extract the X and legend areas. Since the results can have mistakes, so we involve the user to help validate the detection results. After that, Mystique teases apart the main chart content from the reference elements, decomposes it into layout components, and generates a sample dataset as well as the reuse steps at the same time, which happens in the backend. Lastly, Mystique provides a wizard interface shown in the demo and guides the user through the reuse steps to obtain the repurposed new chart. Next, I will focus on the last two stages, so-called GREC-based chart decomposition and guided chart reuse. So what is GREC? GREC refers to grouping, spatial relationships, encodings, and graphical constraints, four semantic components we propose that can jointly represent the overall layout of a chart. Taking this diverging stack bar chart segment as an example, grouping refers to the semantic hierarchical clustering of rectangles and rectangle groups. Here we have two rectangle groups 1 and 2, and they together form a final level 2 group. Spatial relationships estimate the relative placement and organization of same-level rectangles or groups. For example, group 1 and 2 internally both have a stacked relationship, and they together are of a grid relationship. Encodings specify the mapping between data attributes and visual properties of rectangles or groups. Here, the width of each rectangle is encoded with some data value. Lastly, graphical constraints enforce special requirements on the spatial arrangements of rectangles or groups. In this example, group 1 and 2 are vertically aligned by the middle of their gray bars. These four components together define the layout of this diverging bar chart. Since the grouping and relationships are closely related, we first apply a bottom-up hierarchical clustering algorithm to extract them, where the distance function is defined to capture the spatial relationship between two graphical objects, and a linkage function is designed to iteratively merge graphical objects into higher-level ones. Again, taking a diverging bar chart segment as an example, which has in total 8 rectangles. First, we calculate the symmetric distance matrix, recording the estimated relationships between each pair of rectangles. Then, we extract the common relationship, which is horizontal stack that happens to each rectangle, and merge the rectangles based on this relationship into two groups, C1 and C2. The algorithm continues to construct the distance matrix for the two groups, then extracts the vertical grid layout and merges the two groups into one, which is the final collection, whose grouping and relationship hierarchy is shown by this node link tree. This GREC-based decomposition works for a variety of designs, including glyph-based bullet chart and position-encoded Gantt chart shown in the last two columns. Once the grouping and the relationships are extracted, encodings can be extracted with certain roles shown here. We further extract mainly two kinds of alignment constraints within glyphs and on-stacked rectangles. Please refer to the paper for more details. To prepare the reuse UI, Mystique first estimates the required number of nominal and quantitative data attributes based on the GREC decomposition results, then generates a sample dataset for the user to inspect. Then, Mystique follows generally the ordering of groups, marks, then encodings to generate the reuse steps in the UI, and uses Mascot.js as the backend engine to update the editing visualization in real time. For evaluation, we first conducted a quantitative study. To achieve tool-agnostic reuse and promote generalizability, we decided to collect our own corpus, and during collecting, we weighed more on diversity than quantity. The final dataset consists of 150 SVG charts produced by 25 tools, encompassing 17 chart types, 7 small multiple designs, and 3 superimposed views, and 9 bespoke designs. The figure here shows the breakdown of the corpus, where x-axis is charting tools and y-axis is charting types. On this dataset, we have achieved more than 85% accuracy for reference element inference and around 96% accuracy for layout decomposition. Please refer to the paper for more details on the dataset and how the training and test submission is managed. We also conducted a user study to evaluate the usability of Mystique. 12 remote participants with varying visualization creation experiences were recruited, and 4 tasks covering different chart layouts were assigned. From the results, all participants could complete almost all tasks with only a few failures. Regarding the system's efficiency, convenience, and their comfortableness and confidence when using the tool, the participants on average gave high scores. We also gathered some feedbacks from the participants. They are positive on Mystique's usability and their understanding of the tool, but also have raised certain aspects that can be improved, such as better instructions and more flexibility. We expect the future version of Mystique will be able to handle composite visualizations and algorithmic layouts, have smart human-in-the-loop handling of layout deconstruction errors, and generalize to more types of marks. With that, I would like to thank my co-authors again. Feel free to play with Mystique on our online demo website and contact me if you got any questions. Thanks for listening.